All right, we are recording. I am hoping, Lane, Filippo, Mackenzie, that you are watching the video. So let me tell you what's going to happen. We were going to take this quiz today, but there's only one person in the room. So rather than have 3 people needing to make it up, this quiz will be the next time that I am here, which I expect will be tomorrow. Grandbaby is not here yet. Grandbaby should arrive tomorrow, but I should be dropping the little girls off at school. If you get here and my door is still locked, go to the conference room. I should be on my way. Okay? So, anyway, this I should be giving to you tomorrow. The unit circle test is tomorrow, so expect me to time you on this guy first and then throw this at you second. All right? Get those out of the way. What else do we have on our list of stuff? Don't forget you've got the major word problems due Friday on clean paper. Mackenzie, I think you may not have gotten this one yet. Do you have this? Okay. And that's the word problems, formula quiz, unit circle test. That's everything that's listed up on the board for coming up. All right. So let's then just continue with our notes on 4.1. Also, so I do plan on missing a day again this week to go see this new grandbaby. So I have redone my sub notes, and there is a packet in there which is called Unit 3 practice problems. So it's to keep you practicing Unit 3 problems because Unit 3 is going to be on the next test when we get to the end of Unit 4. All right, so anyway, let's continue because we just barely started looking at how we're going to graph these waves. And this first section is just the sine wave and the cosine wave. So when the bell rang, well, let's just stop for a moment now.
We have so many that are testing. We will hang on to the students in that testing room until we have further notice. Okay, so hang on to your students, do not release them. It is now time for the announcements.
Good morning. Please rise for the pledge.
Do you think we should pause this? No, they can just listen to the
I
announcements.
pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Now the Texas flag. Honor the Texas flag. I pledge allegiance to the Texas, one state under God, one indivisible. Please remain standing for a moment of silence. Thank you. You may be seated. We do not lock doors open on this campus for any reason ever. If you see a door propped open, please close the door for our safety. And teachers, please check for dress codes. If there are any issues, please send the student to the office. Monday, March 3rd kicks off National School Breakfast Week. As an incentive, we will give a cool chocolate slushy patch on Friday for every child that eats breakfast in the cafeteria at least 4 days that week. Please don't throw food or drinks and pick up after yourself. Also on Thursday, the cafeteria will have a visitor from Region 5 Nutrition Services. We are asking all students to be on their best behavior. Remember that the state requires at least 3 meal components, and one of them must be either a fruit or vegetable choice to be free to the student and paid for by the state. Please remember that your behavior represents our school. Today's Employee Appreciation Day and Toy Soldier Day. Thank you. Have a great day.
I'm guessing, yeah. All right, so we were just saying last time I taught, which I'm guessing was last Friday, okay? If you're looking at the sine wave, all right, we kind of mapped it out, but kind of follow, which is going to be a pain because there's a lag in the video, but I'll try to do this with both hands at the same time. If you had this point P and it was going to travel positively around the circle, then at the very beginning, all right, you would have it at 0, okay? As this point goes up, on this graph it's going around the circle, but here it starts rolling out. This point P gets higher and higher and higher and higher until it hits the top of the circle, which is at, let's note that, that is 1, and this low point is at -1, okay? Then as it starts to come down, it continues rolling out across the x-axis until it hits 0 height again. Then it starts to go underneath until it reaches the lowest point at -1, and then it continues to roll around the circle until it gets back to 0. So that's what is happening. We're putting this going around the circle, which is a circular motion, into a linear motion. And then if it went around the circle again, we would repeat that. And so the sine, one piece of it, or one equivalent of one circle, is called a period. And you are going to need to think this picture. So whenever you are graphing sine for the rest of this unit, I would recommend, a lot of times students will draw a little x, y, and draw out this little curve that is going up, back to the middle, down, back to the middle, okay? So that is one period. That period would repeat itself every time you went around the whole circle again. So the period takes up a width on the x-axis of 2 pi, because it doesn't start the whole cycle again until it's gone around the whole circle, which is 2 pi. This is real important, so we will have to figure the width of the period. We will do all 6 trig functions on the graphs in Unit 4. So sine, well, let me back that statement up. Almost all of them have a period equivalent to 2 pi. The period is how far out do you have to go before you duplicate that picture again, all right? If it's going to start doing the same thing again, then you've started a new period. The only ones that do not have a period of 2 pi are tangent and cotangent. And their period is just a single pi before the picture starts repeating. So that's going to be important for you to remember. All right, another very important word that we will talk about a lot is the amplitude. Amplitude is the height of the function from the midline to the highest point. So I'm going to take a pink highlighter and I'm going to highlight my midline. This midline was, this graph hit that midline when the height was 0. All right. In the parent function, because we are going to transform these just like we transformed all of our different parent functions from the first semester in college algebra. We transformed square root functions, and we transformed cubic functions, and we transformed quadratic functions and absolute value functions. We will have those same sorts of transformations with all of our trig functions. So this simple little equation is your parent function. All right, so as we transform these, we might shift that midline up. We might shift it to the left or right. We might vertically stretch. We may do all sorts of things. We may horizontally compress. We're going to do all sorts of things to these graphs. So you need to keep in mind, what does the parent look like? And just one little period in your mind is enough to get you going there. You need to know how wide the period is with the parent. In this case, it's 2 pi. And you need to know the amplitude. Amplitude is not the lowest to the highest. So the amplitude is not 2 units here. The amplitude is from the midline to the highest point or the lowest point. And in this case, the amplitude is going to be 1. Now, I'm going to write that amplitude is the absolute value of A, and in this case, it's 1. So, you may think that I'm giving you A because A stands for amplitude, which is convenient, but it's not. Do you remember from last semester when we did transformations and we would have a function and we would have an A value in it? Do you remember what that A value would do? If it was negative, it would flip the whole thing upside down. But if it's greater than 1, it would stretch it. So if I write a formula, and we're going to, on the next page or so, get to how the transformations look in these sine and cosines. But A here is going to affect your vertical stretch or compression, just like it did in algebra. Well, if I vertically stretch this, if I have the leading coefficient as a 3, then this graph would stretch much higher, all the way up to 3, all the way down to -3. So A, think of it as amplitude, because that's what we call it, but also think of it as your vertical stretch and compression factor. That's why I'm putting an absolute value, because you might have a negative A. The negative flips the whole graph upside down. The A is the stretch factor. So if you are asked to give the amplitude, give it as a positive number always. All right. So you can also find the amplitude using the formula highest point, in this case, which is 1, minus lowest point, which is -1, divided by 2. Well, what happens if you have 1 minus -1? It's 1 plus 1, which is 2, divided by 2 is 1. I don't ever do that. I just look at the graph and I go, oh, from the midline up to the highest point is so many units. Or I look at the equation and I pull out the A value. But that's just an optional thing to know there. All right. Knowing that this graph could go on, and by the way, we generally don't put arrows on the end of this graph, although it goes on, because if I drew an arrow on the end, you might think it was more like a polynomial graph and just it's going to keep going up and up. So we just have to understand these go on forever. So knowing they go on forever, what do you think the domain of this graph is? It is all real numbers. There are no domain restrictions with sine and cosine. Every x value is an option. Now, trig does have some domain restrictions, and they will happen with tangent and cotangent, because tangent is the ratio of y over x, right? Well, what if the x value is 0 and you have a 0 on the bottom? That's going to create a vertical asymptote in tangent. And the same with cotangent. Cotangent is x over y. So if the y value was 0, you would have an asymptote. So we will not have a domain of all real numbers on all of our functions. But for sine and cosine, it is always all real numbers. Secant and cosecant also have asymptotes. Now, your range for this parent, how low does this graph go? What's the lowest y value? And what's the highest y value? So that would be inclusive. Every point from -1 to +1 is a y value here. All right. Another thing I'm going to ask you every time I introduce you a new trig function is whether it is even or odd. So we went over this in college algebra last semester. We looked at the graphs, and we also looked at the definition of even and odd. So let's come to this little box, which is here for the purpose of reminding us about even and odds. Algebraically, an even function, do you remember this? F of x is equal to f of negative x. Okay? But odd, f of negative x is equal to negative f of x. All right? Now that probably is ringing a little bit of a bell, but you're probably not thinking about it. All right? If you look at this, f of x is your original function. F of negative x means you plug in the opposite x value. We can look these out in the table that I have up at the top. So take a look up at these tables. Okay? In these tables, I have what would happen if I plugged these values into the function, and I have what would happen if I plugged the opposite of those values into the function. So check it out. For 0, it's 0. But if I went to pi over 2, when I went to pi over 2, my height was 1, wasn't it? When I went to negative pi over 2, my height was negative 1. So when I plug in the opposite input, I get the opposite output, don't I? So let's go down. You can't see these both at the same time. Remember that. Opposite input gives me opposite output. Look at these. Okay? Opposite input, because I have a negative in the x where I do the input. Opposite input is giving me opposite output. That's what an odd function looks like. In this case, opposite input, I might wish I had typed these backwards, gives me the same output. That would be even. All right? Another way to tell if you have an even function or an odd function, an even function would have y-axis symmetry. This is what my one little parent, one period looks like this. It starts at 0, goes up, down, up. It is not symmetric about the y-axis making a big mustache, is it? So it's not a y-axis symmetry. So the other option is, if it is odd, again, I'm going to draw my little one period of sine. It starts at the origin, goes up, comes down low, comes back to the beginning. If it has origin symmetry, then if I rotate it 180 degrees, my hand is in the way there. Let me see if I can do that better without my hand being in the way. Okay, if that rotates 180 degrees, then on the other side, oh, it is so slow to focus. It should look like this on the other side, and the graph, let me turn it back up, should look like this. Is that what's happening here? Let's check this out. On the one we drew, all right? Burn this first one into your retina. So you're looking at what I have in yellow. If I rotate it 180 degrees, do I have that same thing? All right, so because of this, this function is odd. All right, so that's a bunch of information about the sine wave. So we're going to flip the page, and we're going to gather the same bunch of information about the cosine wave. Now, cosine of x I am asking you not to get the sine of x, but the cosine of x. So what are we thinking about when we think about cosine? What kind of values? X values. You know what? I had not made that big. So you could have a little bit more space to work with there. Okay, so we're thinking about our x values. So I'm using the very same inputs, going around the circle in a positive direction. And then over here, I'm going around the circle in a negative direction. So in this case, I'm going to have the opposite input, just like I had it on the previous page in that second section of the chart. And we'll see if it gives us an opposite output or if it gives us the same output. So, all right, remember, you were looking for your x values for your outputs. So when we have 0 radians, what's the x move that I made? What x move did I make to get to here? I moved to the right 1, okay? To go to pi over 2, what x move did I make? Nothing. To get to negative pi, to get to pi, what x move did I make? Negative 1. To come down to 3 pi over 2, what x move did I make? And coming back to 2 pi, the x move is 1 unit, right? All right. I don't have 0 on the chart twice because I already covered it, right? So let's make some negative angles. If I go from the origin to negative pi over 2, what's the x move?
0.
If I go to negative pi, what's the x move? If I go up to negative 3 pi over 2. And if I return to negative 2 pi, which is the same as 2 pi, which is the same as 0, my x move is, now, for future purposes, down at the bottom of the page when we have to choose even and odd, look at this table. This time, what did the opposite input give me? Did it give me opposite outputs? No, it's the very same thing. It gives me the same output, which tells me what about this graph? Is it going to be even or odd? It's going to be even because f of negative x is the same as the f of x, even. All right? That means when I draw the graph, it's going to be symmetric. I could fold it right down the center and the negative side would fold over and match the positive side perfectly. Let's get these points in place. This time, let's do the very same thing. I believe I put 1 and negative 1, 2 squares up and 2 squares down, so that we're on the same page. Okay? So, when I'm at 0 for my angle in radians, I start up at 1 this time. How is that different from the sine wave?
Because it was 0.
Sine wave started at 0 and started to go up, didn't it? Well, let's go as if we're going around the circle in a positive direction. Let's go to the right side. At pi over 2, we should be at, okay? At a full pi, we should be at a negative 1 because that's an x move of negative 1. When we get down to 3 pi over 2, we are back at a 0. And at 2 pi, we are back where we started. This period is 2 pi because that represents going around the circle one whole time, and if you kept going, you would repeat everything. Now, in this case, these are curves. It's not a sharp V. It's curving, coming down, kind of flattening out a little bit at the low point, curving through those zeros, and coming up to here. This is one period. If I picked that curve up, to me it looks like a valley. Okay? If I picked that valley, the entire piece up, and repeated it over here, it would just continue, and it would look like a sine wave. But it's a cosine wave. All right? It's just a sine wave that's been shifted over a little bit. If I go to the negative side, all right, negative pi over 2 would put me back at 0. Negative pi would put me down at negative 1. Negative 3 pi over 2 puts me back at 0. And negative 2 puts me up at 1. It's the very same valley shape being repeated. But now, can you see that it has y-axis symmetry? Yeah, it folds. All right, so that makes it even, correct? All right, what's my amplitude? How high does this go from my midline? Okay. What's my domain? It's just repeat and repeat and repeat as long as I wanted to keep going round and round and round and round and round that circle, either in a positive direction, counterclockwise or clockwise. I would just make more valleys.
Right now the internet is down. We are getting that handled, so just hang tight. Thank you.
So does that mean this is recording? It is, because it doesn't need the internet to record because it's recording and saving into my computer. And then later we'll see if the YouTube is in the mood for me to load this up. Okay, so I don't like how I drew that. So yeah, I'm fine with how I drew that, actually. I'm fine, okay? So if I am going to get a picture of one period here, it starts high at 1. It ends high at 1. Halfway through, it's down at -1. And then the quarter points are at the zeros. So this is what you need to have in your mind as what does a period of cosine look like? It starts high, it's a valley.
Okay, we have a solution. Students sign out of DMAC.
They're trying to do their test online.
Input your information and see if that works. Thank you.
All right. So, have we answered all the information on this page?
No.
Okay, what am I missing?
Range.
Oh, my range. My range. Okay, thank you. All right. Can't imagine how I got distracted here. What is our range?
-1.
Candy's right behind you. -1 to 1 inclusive, because we definitely touch that high point and we definitely touch that low point. So now that you have the very basic beginnings of sine graphs and cosine graphs, we're going to start doing a little bit of stuff with it. So in this section, what are we on, Unit 4? 4.1, we introduce some of the transformations to the parent graphs. And in 4.2, we introduce further transformations. So they give us 2 whole sections to just wrap our minds around all the transformations we may see. But you should see huge similarities between transforming these parent graphs and transforming all the parents from algebra. All right, because it's the same rules. It's the same rules. All right, so what do you think a leading negative would do to your parent? All right, so previously, if I had given you a quadratic, it would flip it over which axis? The x-axis. It would reflect over the x-axis. So let's do a real quick refresher of what does the parent sine look like and what does the parent cosine x look like. if I just were to graph one period. So where does sine begin? Okay, and then if I'm moving to the right, what does it do?
It goes up and then goes down and then stops at 0.
Okay, so that's what your mind needs to go when that's what I'm looking for when I'm looking for sine. How is cosine different?
It starts at 1.
Starts at 1 and it slowly goes down, makes a valley, comes back up, correct? So with that in mind, all right, what do you think a negative sign is going to do? Now first, I have marked out the units on your x-axis to go to 2 pi, but I did not mark anything on the y-axis. So I am going to suggest let's let 1 and negative 1 be 2 units. But honestly, if you get a graph that doesn't have a y-axis, you can make your decision about what you want. You could put 1 up at the top. You just need to label it's 1. Yours will look like it's stretched more, but it's just used a different measurement scale. Okay? So this is my negative sign. I am flipping this over the x-axis, so anything that's above will go below. So I'll start at the origin, but what am I going to do at pi over 2? Where will I be?
Down.
I'll go down first, then back to the middle, then up high, then back to the middle. So a negative sine wave is reflected. All right? Using the same y scale as the last picture and the ones on the previous page, I'm using 2 squares to mark off 1 unit. Where will I begin my negative cosine? At negative 1. The high point will be at the very center and will be at that low point again out here. And so that's my halfway. And I like to call these my quarter points. On cosine, my quarter points are at my zeros. So instead of a valley, we're making a hill. I don't want to call it a mountain. It's too curvy for a mountain. It's a hill. Okay? So let's change some other things. So let's talk about changes to amplitude and changes to period. And so now we're going to start to see what we can change from our parent. So we will be throwing in an A value, which will always be your leading coefficient. And we're going to throw in a B value, which will be the coefficient of your x, which will be inside the argument. When I start putting other stuff than just x in the argument, I've put parentheses. I don't think they will always put parentheses. If you look at this example, they just wrote cosine. Oh, where am I? Got to scooch it down. Cosine 2x. They didn't wrap parentheses around that argument. But if they decide to shift it right left and make a binomial as the argument, they definitely will use parentheses. And we'll see that further in this packet. So remember, a leading negative, that's not really your A. But if you do have a negative in front of your A, you are flipping and changing your amplitude. All right? So we're going to see what happens if I change A and if I change B. Changing A affects your amplitude. It'll give you either a vertical stretch or a vertical compression. Stretches come if the A value is higher than 1. Compressions come with values between 0 and 1. So my directions here are for you to graph the parent y equals x below. We're going to do it first. This time I have numbered the y-axis for you. So I am going to, for me, I'm going to use red to graph the parent. And what is the amplitude of the parent, y equals sine x, when I don't see an A value? Okay, so A equals 1. This time 1 is right here, isn't it? So I have a full 2 pi. I'm graphing the sine wave, okay? And the sine wave normally looks like that, correct? So I'm graphing the sine wave, so I would begin at the origin. I will hit 0 again halfway through and at the end.
Okay, we have reset B-Hall Internet, so try signing in one more time and let's see what happens.
What the Deweyville? Okay. What happens at my quarter points on sine? Because I'm at the 0, the midline, at 0 pi and at 2 pi. But what about these quarter points?
1.
Okay, it'll be at 1. Not quite as high as when we drew it last time, right?
Yes.
And the only difference here is I changed my y scale. So this one is a lower sloping curve, all right? But this is my parent. Y equals the sine of x. My directions want me also to graph y equals 2 sine of x. So what's the amplitude on this guy going to be? 2. All right? So it's going to have the same beginning point. It's going to have the same middle point. It's going to have the same ending point. But my highest height is twice as high, isn't it? And my lowest low is twice as low. And so I make a more vertically stretched sine wave. Now, don't get confused. This looks like what we graphed on the previous page, right?
Yeah.
So why does our 2 sine x look like what it looked like on the page before?
We've been doing that too.
I changed my scale. I've changed where 1 is. And I have that power to do if somebody doesn't do it for me. So always check how they are numbering the grid, the x-axis and the y-axis, and whether you have to make those decisions or you have to follow their decisions. All right. Next, the b value here affects your period. And so that's going to stretch you or compress you horizontally, okay? Which makes sense because the b is grouped with x. And so whatever is grouped with your x affects the x-axis. What did we learn last year about anything that is grouped with your x? You're always going to do the opposite of what you think. Okay? So if I put a 2 in for the b, it doesn't get stretched twice as wide. It gets compressed to 1/2 because it gets compressed to the reciprocal of it. But that's okay. You don't have to think so hard about it because we have a little formula. Okay? The p, what does p stand for? Your period is going to be affected by the b in this way. On the numerator, you put the period of your parent function. Well, our parent functions still are just sine and cosine. So what is the period of sine or cosine? No, not the amplitude, the period. So how far out did we go before we repeated ourselves? 2 pi, a whole circle around the graph, right? The unit circle. So 2 pi is the period of this parent function. It is also the period of sine, cosine, secant, and cosecant. The only time your parent period is not 2 pi will be tangent and cotangent, which are coming up in a later lesson, and those will just be pi. All right? And the b value goes on the bottom. So if you are asked what is the period when you're looking at an equation, you can find the b value in the equation as the coefficient of the x. So if you need to know the period, you just do a little bit of math here. Use this formula. All right? Likewise, sometimes You know the b value because you can see the graph and you can figure out the period, but they may say you need to write the equation, which means you need the b value. Well, you can swap those, right? And you can say, well, if I need to find the b value, I can just take 2 pi and divide it by the p, the period. This is good if you have a graph, because you can just look at the graph and count how many units it's wide till you get this entire sine sweep or cosine valley. But if you have the equation, you can look in the equation and find b as the coefficient of your x. So they want me to graph a cosine wave. I use the exact same grid here as I did in the previous problem. So I'm going to, let's see, I used red here. I think I used, that looks like black. This looks like it's going to be a blue pen, but it is writing black. Okay, back here I used black for my transformed equation. Maybe I should highlight those. That was the parent. I'm going to highlight it in red, yellow, and done. Oh, I have a green highlighter in here. So this was the transformed equation, and this was the transformed graph. So over here, again, I'm going to use green to highlight my transformed equation, yellow to highlight my original. So, graphing the parent, where do I begin with cosine? What's my little takeaway on cosine? It's a valley, right? So I start at 1, which is not as high as it used to be. I end at 1. Halfway through at pi, I will be down at -1, and my quarter points are the zeros, so I have a very low sloping valley going there. That's my original. I shall highlight it in yellow. Now, let's see what happens when we change the b value. So looking at this green equation, what's the b value? It's the 2. Well, to find my period now, you might think it's going to be twice as wide, and I'm really stretching that valiantly out. But remember, it's with the x, so it's going to be the opposite. My period normally is 2 pi for cosine, but I'm dividing by 2, so it's just going to be pi. So I am going to accomplish this entire curve in just pi. I really feel like the starting bell just happened. Oh, we are, 3 pages into the notes here, so we've gotten somewhere. All right, wow, that was quick. I'm going to stop this video.